Welcome to Math 8, Unit 7, Lesson 9, describing large and small numbers using powers of 10. Today we start talking about the early stages of scientific notation. So this will be a method that's used to talk about how we take any decimal value and multiply it by some power of 10 to get a value to be able to express very large or very small numbers. In order to understand this better, we need to understand how the powers of 10 work. First thing we work with is thousand, million, billion, trillion. We need to match each of these expressions with its corresponding values and words. So when we look at 10 to the third power, the first thing that we should be thinking about is that negative exponent. That negative power indicates that we have a number that is less than 1. So we need to be thinking about a reciprocal of 10, or we need to be thinking about 1/10 raised to the third power. When we think about 1/10 raised to the third power, well, we know that 10 to the third power is 1,000, and so we would not to understand that 1/10 to the third power should be 1,000th. So if we were to look at this, and we would call this one A, I would call this one A, and then we would have to look at this piece and say, what is this one? Is it trillion, centi, thousand, million, milli, or billion? The important thing to know about these ones is the only ones that are less than 1 are these two values right here, milli and centi. Centi, we can think about centimeters. Milli, we can think about millimeters. There are 1,000 millimeters in a meter and 100 centimeters in a meter. And so we understand that 1,000th would be milli. So there's an A. 10 to the 6th power, we can go ahead and write that out if you want to, but that would be 1 times 10 6 times. Such as that. We can understand that 1 times 10 would be 10, 100, 1,000, 10,000, 100,000, 1 million. So if this is item B, we find 1 million, and then we find 1 million. And then we just continue on with these things. 10 to the 9th power is 1 times 10, 9 times. Well, we know that, notice right here that we had 6 place values after the 1. So this one, the power of 10, we can notice that there's 9 place values after the 1. 9 would be a billion. So this is C. And we mark this one C. 10 to the negative 2. Here again, we have the negative exponent or the negative power. We recognize that as 1/10 to the negative 2nd power. 10 to the 2nd power would be 100. So 1/10 to the 2nd power should be 100th. And this would be our centi value. 10 to the 12th power, this would be a 1 followed by 12 zeros. We recognize this one right up here would be 1 trillion. So this is E. And then that leaves us with 10 to the 3rd power, 1 times 10 to the 3rd power, which ends up giving us 1,000. There you go. On the next page after this one, it says, for each of the numbers, think of something in the world that is described by that number. Oh, sorry, just kidding. That's up here. For each of these numbers, think of something in the world that's described by that number. Well, a trillion, let's just start right at the top. A trillion, or we'll use these words right here. Billion, this is probably something that we look at like followers on social media, that everybody wants to get up into the billions because then they make lots of money. Then they can make billions. Milli, we already talked about millimeters. Whoops. You could talk about a millipede, things like that. Million, that's kind of the reality of the number of followers that are out there, but million also describes a lot of different pieces with money, and we could talk about this, like we could say followers, we could talk about several different things with that. 1,000 is typically associated with money. It's also associated with different products for when you sell the products. Centi, centimeters. Trillion, national debt. Not a lot of things get up into those values of the trillions, but that's a spot where we can definitely think about real world numbers that describe those numbers. In the next set, when we talk about base 10 representations, When we're talking about powers of 10, we're really working with the base 10 system. And when we talk about base 10 system, we are talking about our number system. We have the digits in our number system are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Our base 10 system is called base 10 because we have 10 digits that represent our system. And just for a fun fact, why do we round numbers when we go past 5? Well, that's because when you look at this in our values and our sets of digits, if you're rounding a value and you get to everything we understand is up to 4, it stays the same, and anything 5 and up, we round up. Well, this is the reason why. It's because when we talk about our digits, when we get to 5, we're more than halfway to the next digit. So just a little thought there. Number 1 here is match each expression to one or more diagrams so that it could represent it. For each match, explain what the value of the single small square would have to be. We talk about here is A, B, and C. These are the different graphs or the different images that will match up with these ones right here. We have 2 times 10 to the first, or 2 times 10 to the first power plus 4 times 10 to the negative second power. When we look at 2 times 10 to the negative first power, we're looking for something that's going to be looking like 10 times 1/10, or 2 times 1/10, I'm sorry. So we're looking at something that's going to be a little bit smaller, which would be 1/10 the size of 2, which would give us actually 2/10. Okay, we're going to add that with 4 times 10 to the negative second power, which is 1/10 times 1/10, or just 1/100th. And so we're going to add this one to 400ths. This would be a way to be thinking about these pieces, and then we have to decide how would we add these values up, or what would we use together. These expressions to one or more of the diagrams could represent, well, let's look at our diagrams. We have A, we have 100 grid, and 1, 2, 3, 4 individuals. Sorry about that. Another 100 grid, and then 4 tenths. And then looks like a 10th strip, a 10th strip, and then individual ones. So which one will match up to this one? Hold on a second. I'm going to pause. I got somebody that's trying to get my attention. All right. Thank you for your patience on that. And sorry for the break there. Where we're at with this, we talked about these pieces, looking at the values of A, breaking this down 2 times 10 to the negative first power. We can go ahead and match that up with one of these pictures down below. So what we really want to seek with this is having that understanding of what would be 2/10 and what will be 4/10, and the total with that being 42/100. And so if we look at 42/100, recognizing that the entire grid is 100, this will be 10. Each of these tall strips will be 1/10 of the whole. So we could look at this as 1 whole, 1/10. And then that would make these other ones here 1/10, 1/10, and 1/100th. And when I match those pieces up, I can see that this would represent the 400ths, and these two would represent the 2/10. And so if I look at 2/10 plus 400ths, I get 42/100. So we can match up C here when these are tenths and hundredths. Okay. The next one that we want to look at, let me get rid of this just in case. For the next one. The next one we want to look at would be matching the same type of thing. We already know that 2 times 10 to the negative first is 2/10. And now we already know, or we know that 4 times 10 to the negative second is 400ths. But now we're looking at 10 to the negative third. So this would be 4 times 1/10 times 1/10 times 1/10, which would be 4 times 1/10 is 4/10, 400ths, 4,000ths. And so we see this would be 4/10 plus 4,000ths, or a total of 204,000ths. When we think about 204,000ths, where will we get the 200? Well, we can talk about those values. I think that this one has the 4 individuals, and this has 4 individuals. So I don't think it'll be B, because that would be an indication of 4 ones. even though it's 204 thousandths, those are kind of like the ones place with that thousandths, the number. B is out. C, it won't work. But when we look here at A, this will be a 100th, or excuse me, this 100 right here could represent the first value of the tenths, and then another tenth, and then we get to the 4 thousandths because we're looking at the small squares as 10 to the negative third power, or each as 1,000th. So there's 200 thousandths right here and here, plus another 4 more. We would match this one with A. 2 times 10 to the third power would be 2 times 1,000, plus 4 times 10 would be 4 times 10. So we have 2,000 plus 40 would be 2,040. And then when I look at this one, I can recognize that same piece with this and say, well, if we're looking at these values as I go in this, which one could represent that again? I'm probably going to go to this one right here, or excuse me, B. No, I'd go with A. This one right here, because these ones could represent the 1,000 piece. And then you're saying, well, how could that be? Well, if each of these little squares represent 10 to the first power, that would be 10 plus 10 plus 10 plus 10. And then each of these would be 10 to the 10, or 10 to the first power, which would make that 10 times 10 is 100 by 100 to make this 1,000. And then this one again, 100 by 100 would be another 1,000, making that 2,040. So we can match this one with A as well. The last one, if a small square on this one were to represent 10 to the second power, I could make this work for right here, because this is 2 times 10 to the third, which is 1,000. 4 times 10 to the second is 400. And we could see this one as 1,400. When I look at this piece, if I think about these being 100s, there's 400 here, and there are another hundreds right in here, so this would be 1,000 and 1,000. So we could look at these pieces as 1,400. So that one could be C, but it could also be B. If we look at B and we see each of these as 10 to the first power, an individual square equals 10 to the first power, then I can look at that and I could say 10 to the first power would be 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And then that 100 would be 100, 200, 300, 400. And 100 times 10 would be 1,000. So this would be 1,000, 1,000, 100, 100. You get the idea. It's getting really small. But we can write this up right here is when we say C is the little one is equal to 10 to the second power. B, when the little one is equal to 10 to the first power. For A, I should probably mark those in there and say when the little square is equal to 10 to the first. This one, when the little square is equal to 10 to the negative third. And then the first one, when the little square is equal to 10 to the second, negative second, sorry. And I just realized something. That could also be letter B as well. We can make this one letter B when the little square is equal to 10 to the negative third, because these could be each of them as thousandths, and we could see the same thing right there. I would make 420 thousandths or 42 hundredths. That one was a lot. As we move on to this one, we see that I made a mistake. With this right here, I think is where they're, oh, just kidding. I skipped over that one. Here's number 2. It says, write an expression to describe the base 10 diagram in each small square represents 10 to the negative fourth. What would this value of this expression be? So we're saying this is 10 to the negative fourth power for each of these little blocks. What we can see right here is we have 4 of those values. So 4 times 10 to the negative fourth. For the next piece of it, if this is 10 to the negative fourth, then this would be 10 times 10 to the negative fourth, which would be 10 to the negative third power. We have 5 of those. That would make this 10 to the negative third because each of these are 1,000th of the value. So this would be 10,000. These would be 10 times larger than the previous. So we go from 10 to the fourth to 10 to the third, which would make each of these ones right here 1 times 10 to the negative second power and 1 times 10 to the negative second power. We progressively go 10 times larger with each of the figures that are there. So 1 square would be 10 times larger here, 10 to the negative fourth to 10 to the negative third. 10 times larger would be 10 to the negative second. And so the expression that we would be after for this one, we combine these two together, which would make that 2 times 10 to the negative second plus 5 times 10 to the negative third plus 4 times 10 to the negative fourth. And we see our progression getting 10 times smaller each time. So just for a by the way, that value would simplify out to 254 10,000ths when I add those all together. So how does the changing of the small square change the value of the expression? Explain or show your thinking. Well, when we change those values of the small square, it changes the power of 10. So changing value of small square changes the power of 10. When we look at that, if we talk about that long rectangle, if it has an exponent of 1 higher than for the small square, then the larger square has to be 2 higher than the small square. So this one we would see, perhaps if we were to look at this and call each of these a 1, then this tall stack would be a 10 and this would be a 100. Let's say if we called these ones 10s, then the tall stack would be 10 by 10 or 100, and then this would be a 100 by 100, which would make it 1,000. And you get the idea as we go on that every stack or every different figure has to be 10 times greater than the next because it's just 10 times larger. For letter C, we're asked to select at least 2 different powers of 10 for the small squares and write the corresponding expressions to describe the base 10 diagram. What is the value of each of your expressions? Well, if we said that the small square, like we said, is equal to 1, or 10 to the 0 power, which equals 1, we could see that up here above, we would recognize that that is 4 times 10 to the 0 power, plus the next one would be 5 times 10 to the first power, because each of these are 10 times bigger, plus 2 times 10 to the second power. So we get values where we have 1 times, so this would be like saying 4 times 1. This would be like saying 5 times 10. And this would be like saying 2 times 100. And you see the idea of the progression 10 times larger each time. If we said that the little box is equal to 10 to the negative 5th power, then we have that progression where we recognize that this would be 4 times 10 to the negative 5th times 5 times 10 to the negative, plus 5 times 10 to the negative 4th plus 2 times 10 to the negative 3rd. And we see that progression where we go from the smallest value to the largest value is 10 times larger each time. And you might be saying 10 times larger, those are negatives. Yes, but the negative is getting larger. And that might throw you off. It's getting larger because it's getting closer to 0. Okay. 9.3, using powers of 10 to describe large and small numbers. In this activity, we're starting to figure out that powers of 10 can grow and shrink things pretty quickly. And so when we're after this piece, it says that teacher would give you a card to tell you whether your partner A or B gives you the information that's missing. So what we're going to be looking at here is something that I'm sorry we won't be able to use, but it would be something that would be kind of fun. Just a couple of pieces around here. First thing, around the world, about 14, how many pencils do you think there are? There's about 14 billion pencils that are used or that are made every single year. And what we're supposed to do with this, or what we'll come to do with this, is we're actually going to write these in the next statement as powers of 10. Oh, you know what? We're not going to wait. We're just going to do it right here because I think I'm wrong. This power of 10 right here, we would have 14 times 10 to the 9th power. Would be another way to write that word because 14 billion, that's a lot of pencils. If we go to the next one, a mass of a proton, hold on for this one. Mass of a proton would be 0. I hope I have enough room in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I hope I have this right. I don't know for sure if I do. I'm copying this down off something because I couldn't remember what it was. Kilograms. Can you imagine writing that number over and over and over again? There's got to be a better way for that. So one way we can kind of think about it is like this. It's what it should be, 10 to the negative 30th power. That represents how many place values are here. If I was to write this in true scientific notation, this would be 1 and 6700ths times 10 to the negative 32nd power. So just think about that one. Let's go to a number that's a little more reasonable for us. The population of Russia is about 144 million people. Okay. That 144 million, we could say that's 144 times 10 to the 6th power. In scientific notation, that would be written as 1 and 44 hundredths times 10 to the 8th power. The diameter of a bacteria cell, they're pretty little, but they're definitely not the same as the mass of a proton. We see that that has a power like this. We could recognize that that would be 2 times 10 to the negative 6th power. But when we write this in scientific notation, it would actually be 2 times 10 to the negative 7th power. So the negative 6th power, as you probably noticed, counts how many zeros there are. But the scientific notation, we'll get into the definition of scientific notation in another lesson, would include all the way past the first non-zero digit. Okay. Light waves travel at a speed of about 300 million meters per second. This would give us 3 times 10 to the 8th power. If we're talking about the population of India is 1,300,000,000 people. This would be 13 times 10 to the 8th power. In scientific notation, 1 and 3/10 times 10 to the 9th power. You'll notice there is a difference between these two when I talk about scientific notation. Again, we'll get into that piece. When we're talking about the wave of a gamma ray, we're talking about 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 4, 8. We're talking about a number that's like this. So this is 48 times 10 to the negative 11th power. But in scientific notation, we have 4 and 8/10 times 10 to the negative 12th power. And then finally, a tardigrade, a water bear, they're pretty cool. You should go look up what a tardigrade is. And they're this big. They're 5/10,000ths of a meter long, or 5 times 10 to the negative 3rd, which in scientific notation would be 5 times 10 to the negative 4th. Whew. There's a little piece for you. Now, why does it matter that I've done all this work going from these numbers that we can usually write that we might be used to into this form of scientific notation? Well, here's the thing with it. You ever heard of the word Google? Well, Google's a name for a really big number. That's 1 followed by 100 zeros. I am certainly not going to write that because that is just too much. If we're writing this, then we would say that's 1 followed by 100 place values. If you square a Google, sorry, I should have probably put this up here. That's a 1 followed by 100 zeros. If you square a Google, how many zeros will that answer have? Well, if you square that value, meaning that you multiply 10 to the 100th times 10 to the 100th, we would be looking at that value and we would say 100 times 2, because of that power of a power situation, that would be 2 or 10 to the 200th power. That's a lot of zeros. This is our explanation. Show your reasoning. How many zeros would it have? 200 zeros. If you square a Google to the Google power, how many zeros will that answer have? Well, that'd be 1 times 10 to the 100th. And then we're going to raise that to the Google power of 100 again. Then we can simply multiply 100 times 100, and we would get 10 to the 10,000th power. And we recognize that by power of a power, this would be a piece to use with this. So we can use those powers of 10 plus the values that we're using now to be able to recognize that there are some really, really big numbers that are out there. Question is, how can I write them efficiently? Sometimes powers of 10 are really helpful for expressing very large and very small numbers. For example, there were 500 billion pennies that were made by the US Mint. Okay. There's over that many. So how can I write them? Well, if I write them like this using a power of 10, we can write it as 500 times 10 to the 9th. We could also write 500 times a billion as 5 times 10 to the 9th power, or 10 to the 11th power. This is scientific notation. And you might still be asking, what's the difference between that and this? It all has to do with this value here. It's called the finite decimal. We'll get into that definition in a future lesson. But we can look at the same thing. The advantage to using powers of 10 with large numbers is it helps us to see right away that there's a really large number by looking at the exponent. Same thing's true for small values. When we look at this, it's a single atom of carbon, weighs this many grams, 199. I wouldn't know how to say that number without putting a lot of effort into it, but I could say 199 times 10 to the negative 25th power. That tells you that there are 25 zeros here. And then when we look at that value, 25 place values here, when I look at that value and the equivalency with that piece, I have to recognize that this one right here, scientific notation, is the proper way that we would actually write that value. You'll notice that the number in the exponent changed just a little bit. We're looking at not only powers of 10, but we're also looking at ways of avoiding errors in writing this really long number, because just missing one single place value can change the entire outcome of any experiment. It could change the outcome of any budget. It could change the outcomes of anything when there's large numbers in play. So thanks for tuning into the video. Again, I apologize for the break in the middle. Let me know if you have questions and how I can support. Have a great day.